Okay, so we've established that to make geothermal power competitive, we need to drill deep holes, probably many kilometers deep, and we need to drill multiple holes to allow the heat conduction. Just one or two holes don't generate enough electricity to be useful. We just don't get enough power from one geothermal well. We're going to have to drill lots and lots of them. So that's the challenge. You need to be able to drill a several kilometre deep hole in the ground for a price comparable to building a wind turbine. So let's think a bit about some of the challenges of drilling and how it can be made cheaper. So how do you actually drill a hole? Now remember, this is a technology that's been pioneered by the oil and gas industry, so people have been doing it for a very long time. So in the olden days, what you'd do is you'd just, much like drilling a hole in the wall, you'd have a rotating drill bit with some bit at the end, on the end of a long tube, and you'd rotate it at the surface, and that would cause the whole thing to slowly grind its way into the ground. Now, that doesn't work when your drill becomes too long. It might work if you're going a few hundred meters down or even a kilometer, but by the time you're like 5 or 6 kilometers down, you can't rotate at the top to make the bottom drill. It twists the metal too much. So typically you're going to have some sort of motor at the bottom, and you're going to have drill bits. Here are examples of drill bits which will grind the rock, and you'll normally be pumping a fluid down to carry the bits of rock away and then flow back up again. Now these drill bits are carefully designed. A lot of research has gone into the best possible shape for these drill bits to be able to work their way through the rock. It depends what sort of rock you're working through. They're often studded with artificial diamonds, but they do wear out fast. And most drill bits so far have been designed for soft sedimentary rocks, drilling through like limestone or sandstone or shale, because those are the rocks where you find typically oil and gas. Whereas if you're going to do this anywhere in the world, you might want to drill through much harder rocks found in other places, like granite. Now, one problem is casings. As you drill the hole, there's always a chance that the outsides will collapse in on you. So what you'll typically do is you'll put a casing, a steel cylinder around the outside to stop the outside rocks collapsing in, and also to keep your fluid inside. Otherwise your fluid might escape out into the surrounding rocks, or fluid from the outside rocks might work your way into the tube and muck things up. But as you go deeper, this becomes hard, because if you're going to put the casing down at 8 kilometers depth, you have to get that casing down there, which means you need wider casings further up. So for example here, they're talking about having a 21.6 centimeter open hole at 4 kilometers depth. And that means to slot that in, you're going to have a wider hole at 3.6 kilometers depth, a wider still one at 2.8 kilometers depth. So basically you have to drill a very wide hole at the surface so that you can slot the slightly thinner bit into the next bit, and then the thinner bit still for the next bit. So if you're going deep, you're going to have to end up with, in this case, 91.4 centimeter casing at the top. That's nearly a meter across. That's huge. So, which all costs money and time. And big drill bits, there's more to excavate. You're not talking about a narrow hole, you're talking about an enormous hole at the surface to get you a narrow hole at the bottom, simply because you've got to be able to fit each steel casing through the ones above it. And also, if you've got fluids in the rock which have toxic chemicals in them, which is often the case, then you're going to need to make these casings out of expensive alloys of steel, not just your cheap steel, because otherwise it will corrode, and then you've dug this really expensive hole and then the whole thing rusts through. That wouldn't be very good. So that's one reason why it becomes expensive. Another very tricky thing when drilling any sort of hole is pressure balance. Now as you go deeper and deeper underground, the pressure goes up. Basically, if you go down in water, pressure goes up by about 1 atmosphere for every 10 meters you go down. And 1 atmosphere is 100,000 pascals, 100,000 newtons per square meter. And the reason why pressure goes up as you go down is because something has to hold up all the water or the rock on top of you. So basically, the more dense it is, the more the pressure must go up as you go down. So what that means is even a few hundred meters down the pressure is enormous, and by the time you're kilometers down the pressure is just staggering. I mean, a 10-kilometer hole, the pressure at the bottom would be the same as that if you're in a submarine going to the bottom of the Marianas Trench, the bottom of the Pacific Ocean, which is a very dangerous thing to do. You can't send a person down there, the pressure would crush them in seconds, unless they're in some really strong submersible. So the hole can't just be full of air. If it is, the enormous pressure on the outside would definitely collapse it just like this. What you have to do is make sure that inside your hole there is a fluid which is at roughly the same pressure as the rocks on the outside. Otherwise, lots of things, really bad things, can go wrong. This is actually one of the major dangers in drilling for oil. Let's say that you hit a cavity underground where the pressure is much higher than whatever water you've got in your tube. That pressure can then force this boiling water back up and spray boiling water all over everyone at the surface, which is very bad for your health, plus may destroy your drilling rig equipment. Or it could be that if you have the pressure of the water in your tube is bigger than outside, the water can suddenly escape into cavities. Because the density goes down, it might then turn to steam, and suddenly you've got a bubble of steam once again pushing boiling water back up your tube, destroying your rig and killing the people who are drilling it. So it's very important when you're drilling to maintain the pressure of the inside at all depths to be the same as the pressure at the outside, but you may not know that precisely. What they normally do when drilling oil rigs is the fluid that's sent down, which is used to maintain the pressure, and also as it's pumped down it allows you to carry the rocks that are being ground up at the bottom back up to the surface, is usually made of a mud, often a very special mud with rare elements and metals in it, to make sure the mud has the right density so that its pressure increases as you go down by the same rate as the rocks on the outside. And this is one of the most challenging things in drilling oil rig, is to make sure you've got the right mixture of mud at every point as you drill down to keep the pressure here and here and here and here as roughly the same as the pressure on the outside, so your tube doesn't explode and you don't get boiling water squirted back up at you, or the whole tube doesn't collapse. So these all make drilling rather complicated. One possible solution is to drill into hard so-called basement rocks. Almost everywhere on Earth, if you go deep enough, you get igneous rocks like granite. This is not where most drilling has been done so far, because most of that's been done in sedimentary basins to find oil and gas, but that's actually relatively rare in the world. Most places there's nice hard basement rock like granite. And these rocks are hard enough that you may not actually need casings. They're strong enough and impermeable enough that your water probably won't leak out or in. You can just actually use the granite wall. Also, in these rocks, typically the pressure increases as you go down at about the same rate it does in a column of water. So you can just use water to drill rather than some exotic mud with metal elements put inside it. So drilling granite might be quite easy. You might not have to worry about the casings. You might just be able to use water rather than exotic muds. But you're going to need really tough drill bits. And people haven't really researched the drill bits to drill through granite. Granite's a hard, abrasive rock. You also, if you're going really deep, you're going to need drill motors that work at very high temperatures. Most of the existing motors are not designed to work at those sort of high temperatures. You either need to somehow cool the motor that's doing the grinding, or develop a motor that can work at temperatures of 200-300 degrees, and most current ones can't. There's no obvious reason why you cannot build motors that work at high temperatures. It's just not been needed so far. And some people have speculated about exotic drills rather than using, for example, rotating diamond bits to grind out the rock at the bottom and then pump it back up to the surface. You might use things like a plasma or a laser drill, which might actually have the benefit of melting the side of your tube to give an even more casing-free hole. So these are some of the research directions. Can we make better drill bits with motors that work at higher temperatures, or is something exotic going to be useful to drill these really deep holes? But it might well be that drilling into hard basement rock like granite is the way to go, which opens up far more of the world for this whole geothermal power. So, where are we right now with geothermal? We know that except in places with hot volcanic springs near the surface, geothermal power is currently not cost competitive with any other form of power. So the hope is that by researching, for example, better drill bits and better ways of enhancing the heat flow and so on, we can bring the price of geothermal down to be more competitive. The trouble is the price of the competition, wind, solar, batteries, is also getting dramatically cheaper every year. So it's not enough for geothermal to get cheaper. It has to get cheaper faster than its competitors. So the idea is we need to get a learning curve going for geothermal. Now this has already happened for a long time. People have got much better at drilling holes because of the oil and gas industry. So maybe some of those same techniques can be ported across to drilling into hard rock rather than soft sedimentary rock. So what must happen? So right now, heat applications make more sense than electricity because the geothermal heat isn't very high temperature, so the kind of efficiency of getting electricity out is quite low. So probably the sweet spot for this is things like district heating and industrial process heat. Another possibility is you can put a deep geothermal well into, say, the ground underneath a disused coal plant. Because a lot of the expense of generating electricity is getting all the turbines. Right now, the turbines in coal-fired power plants are supplied steam by heating water by burning coal. But maybe you can drill a really deep hole and get the hot water from that to flash into steam, and that can drive the turbines, thus saving you the cost of building new turbines. Because, of course, an advantage of geothermal is you can put one whenever you like, so why not put them where you already have a nice turbine that's going to get disused to repurpose it? And that could bring the price down because you don't have to pay for the turbine. So some combination of this, some combination of using it for heat, and some combination of maybe repurposing existing turbines might make geothermal power a bit more cost competitive. And we're going to need something like this because for any learning curve you need to do a lot of it to get cheaper. So we need to find some way to make geothermal economically feasible, maybe just in special situations, and then use that practice from building these things to develop supply chains and develop the technology and bring the overall price down. I mean, if geothermal had started earlier than, for example, solar and wind, maybe that would be cheap now on the solar and wind. If they were using technology from 30 years ago, couldn't compete. But because solar and wind have started decades ago, they've already driven the price very down, so it's hard for geothermal starting now to catch up. Historically, if it had been the other way around, maybe geothermal would be very cheap and solar and wind couldn't catch up. But that's not the way the history worked.